You are probably aware about large language models, but how many of them are there? And which one are better for what tasks? In this video, I'm going over 8 different large language models, and we're gonna discuss a little bit about their difference in architecture and what is the best time to use them. So basically, not only the size matter, but also the architecture matter. We'll talk about the trade-off, cost, latency, the reasoning, multimodality, and whether it can be used to generate actions, and which one we should pick at what time. So this is going to be an interesting video. Without further ado, let's jump right in. Welcome everyone to your channel, AI Fun Fact for All. For those of you who are new to this channel, my name is Pedram. I have a PhD in computer science, and in this channel we talk about AI and machine learning and how we can use it in order to improve our efficiency. As we said in this video, I'm going to talk about the 8 different architectures. So let's jump right into it on the first one, which is Generative Pretrain Transformer, or GPT. So this is something that we early on saw it by the ChatGPT, and basically it's evolved from there. The idea from the Generative Pretrain Transformer, or GPT, come from the whole encoder-decoder architecture, and using this multi-head attention and having a separate decoder one that basically get the results from the encoder to do the cross attention. And we know that some of them are decoder only, same as the ChatGPT one, and they are actually causal LLM. So the whole process is basically left to right token prediction, and they are optimized for generative fluent text generation. So basically they predict the next token given whatever comes before them, and they are excellent at the text, the code, conversational replies, and the whole concept of training of them is relatively simpler. And because you want to have a massive text corpus, for example, something like the whole internet, and then you try to give some causal objective, you might want to mask some part of your words, and then you probably want to do some instruction fine-tuning after that. So why would you use GPT when you want some scalability, a smoothness, chatbot, some easy assistant, code assistant, and you want to summarize? And these are good for long chain of formal reasoning or imaging, and they're good through training of hybrid system. So pretty much a lot of things in the basket, but as you know, if something is generalized in everything, they cannot be the best at one. So the ones that we're gonna talk after this are the ones that are specialized in specific tasks. The next one that I want to talk about is mixture of expert, or MOE. This is the one that you probably have heard a lot about, and these are the skills that you see from lots of the open source ones, because they don't have access to a lot of GPUs. So what they do is that they try to sparse the computation via experts routing. So at each time, each token is basically assigned to a specific expert, rather than firing all of the basically multi-connected network. Only just a specific expert is routed, and it is done per token. And so what will happen is that it's not gonna have that big number of parameters, and obviously it's gonna have a lower compute. So it is a smart scaling trick. Instead of activating the whole network, you learn a router, pick a few specialists or expert, and it has a huge capacity without basically linear computer costs. What will happen is that they are very good and useful when you want multilingual breadth or massive capacity, but you want to have a cost-effective solution. But obviously there should be a cap, otherwise everybody gonna work with MOE. So the problem is the training. The training is a much more trickier, because what will end up usually happening is the mode collapse, which only one of your experts will be trained, rather than having different ones to be triggered on different basically skills. So the load balancing, the loading, the stability are actually some of the most difficult engineering problems. So we'll use MOE when the throughput or cost per token matters more than ease of training. And as you can see, the structure is pretty much the same, but the MOE will basically come on top of the feedforward and add a normalization in here, which basically means that you're not gonna have the normal multi-head attention, and that's all are connected to each other. Only one specific expert or basically a branch is going to be ignited and going to be activated at each time. So what about the next one? So in the next one we have a large reasoning model. So these are the things that you probably have seen on the O1 series for the basically ChatGPT, OpenAI, and there are also other tags that you see, for example, in your Gemini, that you can activate the thinking mode. So the concept of this is that we want to have basically a model that can reason much better. So what you will do is that you try to focus on test time compute. So that's one way, which basically we saw some of the prompting technique, which is chain of thoughts. You try to ask the model to reason when it wants to provide the final answer. But then they extend this concept of test time compute to train time compute, which basically means that they train the chain of thoughts and multi-step reasoning via reinforcement learning, and they generate some intermediate steps before answer, which improve the correctness of complex tasks. So the only reason that we want these large reasoning models is basically if there is a need for larger and longer thinking and reasoning. So what they do is that they produce intermediate reasoning traces, a chain of thoughts, and self-consistency, and RL-tuned policies, which try to basically incentivize generating some intermediate responses that are required in order to generate some response at the end. So basically, obviously, the training gonna take longer. Basically, mostly this one will happen post-training, so it's kind of similar to instruction following a post-training process. And what will happen is that obviously the verbosity is gonna be higher, so it will basically cost latency and also the cost itself. But at the same time, it will yield some dramatically better results on math, logic, planning, and complex debugging. So in case of the situations where you see that we all know that like LLM are not very good at math, so if you want something that excel at that or excel at debugging complex and huge chunk of codes, that's where you need a deeper thinking. So this requires some multi-step reasoning, some formal proof, long logic problems, or planning the agent for the next 20 steps. So these are some LLM style approach. I have put all of these inside the link of the description, so go check it out, and if you want to learn more about them, you can basically see them and download it yourself. So moving on to the next one, we have a vision language model. So as the name suggests, it's obviously when you have a basic system that also requires some information about vision. For example, you want to generate something, or some user actually provide you an image, you want to do some changes on it, or you want to basically ask question from the image. That's where you not only just need the text to be embedded, but you also want vision embedding. So the concept in here is it has a joint image and text representation. So we have vision encoder and text encoder decoder fusion, and then zero shot multimodal capability are the thing that may come as a byproduct. So LLM merge sight and language. They encode vision basically through the vision transformer style. We have so many different concepts that patch the specific basically pixel of the image, or basically use some specific mask to do the attention on vision language models, and basically somehow tokenize the image. And so we have the cross attention, but the cross attention in here would not be between image itself, it would be between image and the text. So you get some visual queries, and then you read documents, caption images, and you want to have some document understanding, for example in a PDF which has a combination of text and images, and you want to have any multimodal agent that needs to see and talk. They make accessible tool and the multimodal agent much more natural, and they require large image text pre-training to become robust. So we have a complete set of pre-training specifically for the vision to basically make them suitable for this sort of task. So as we go from the vision models, we need to talk about a small language model. So small language models, or SLM, are actually a very hot topic right now, and they're actually a good solution for the very fast requirements, or the one that needs to be run on the edge devices for many privacy reasons, or where you want to answer very fast and quickly. So optimized for efficiency and latency, they use the distillation, which basically have a bigger model and then try to distill it to a smaller one, and they use pronings, so if anything is not required they just get rid of it. And obviously the quantization need to be done in a way that doesn't have too much effect on the accuracy. When you have a specific agent for a specific task, SLM actually is a better solution compared to a very large language model. And the reason is, if that agent on that a specific portion only have a specific task, you don't need a large language model generally. So you basically only need a spatial one, and SLM are the best because they have low latency, low cost, and basically generally faster for the response. So SLM are lean, fast, and then big LLMs. So designer cut complexity with grouped query attention. This is one way of basically attention. So we have group query instead of basically multi-head attention. We have group query, which was introduced by Google, and then we have a smaller hidden layers, and then layer deduction, and the whole concepts from how to make it more efficient. So they have the knowledge come from distillating and from a larger models, and aggressively quantized for memory saving. So you don't save the whole FP16 or 32, you try to reduce it to BP16 or so on. So the low latency response and the ability to run on the phone, on edge devices, and obviously the trade-off is the lower capacity, and they're good obviously for the privacy reasons. But after that, we need to talk about some more specialized language models, same as large action models. So action models are actually the big thing in 2025, where we talked about how agents are gonna basically talk and will be seen everywhere. The reason is that we want some output structured and we want it to be accurate as possible. So for example, a JSON that we can use for API calls, or for example design a perception task. So for example, do a reasoning and then act loop, or bridge the intent into some external tool. So we don't want to be confined into some text, we want to also take some action. But in order to make sure that we take action correctly, we need to make sure that the response are actually very much accurate. Basically the level of curiosity or the level of creativity would be a lot lower, and it mostly be on the accuracy. So LLM are action oriented, they just they don't just write the text, they produce executable context, so the level of creativity is lower. So just a call API controlling robot sequence, and a runtime execute these actions till the result the model, and will update it. And the architecture difference for them is that they're essential for workflow automation, digital assistance for the control apps and robotics. Man, this requires a strict validation. So the most important part for these LLM is that you cannot use the conventional BERT or other blue method in order to basically find their similarity. There has to be exact match or basically some other level of validation, so that you are sure that you are generating the response as you are looking for. And after this, we're gonna have hierarchical language models. So these are when you have a bigger concepts and you want to break it down. So we saw that agents can actually pretty much do that. We have a planner, an agent, and then it break it down to some subtask, and each subtask can do it. But this one can actually come inside as a whole LLM package, as what we call HLM. So what will happen is, as you separate the high-level planning from low-level execution, and the structure representation, move between layers, and improve long horizon tasks and reuse of the plans. So basically we break it down into levels. The top layer write a goal or goal decomposition, and the lower level try to execute them, try to focus on one specific task in order to be finished. And there is error propagation, make long task manageable, like for example planning a multi-day project or coordinating a multi-agent system. So it's kind of similar to how human also plan. So you first strategize, and then after that you are trying to run and execute those runs after that. So it is very good for long running workflows and complex multi-turn agents that you want to maintain a consistent long-term context. Same as, for example, you want to generate a cartoon or for example an animation. Well, what you care about is that you want to have a consistency in your visionary inputs on the different scenes. So these are the kind of long context that we are talking about. And after that, we have long concepts model. Long concept models is more like an abstract idea rather than something that is actually generalized and kind of accessible to the public. So it's talk about the concept level rather than token level, and they are using some graph-based representation. So we have something like, for example, a RAG, which are trying to retrieve the information from the structure or sentiment representation, but we have also a graph-based RAG, which basically try to get the information from a graph representation. And these actually are more helpful if only the meaning is not enough. So reasoning over concepts and relationship and research focus improve generalization. So these focus from tokens into concepts. Instead of predicting next forward, they try to think that the high level knows and the relationships, how the knowledge graph, how different abstract concepts are linked and connected to each other. So this actually help for the paraphrasing some domain specific answers, some language, because they operate on meaning units, or you want to have some specific information about the concept that in terms of the purely semantic they are the same, but they mean completely different things. For example, something like somebody owes somebody else, and then you're trying to look for something that this person owes, but then it will try to find something that is vice versa, completely contradicting or deficiting the whole purpose, but from a language perspective it is the same. So these LCMs are large experiments all today, but they're promised for scientific reasoning and knowledge synthesis. The big challenge in here is that how you can integrate this robust concept space into some neural methods. And the big missing piece in here is basically where do we get the data from it. And there you have it, guys. We went over 8 different large language models. We talked about their key architectural differences. What we want to do is that we want to start from the constraint. So we need to see that what LLM do I need to use first? What is my constraint? For example, what if I want to have a low latency? So in that case, I definitely want to work with an SLM, because SLM are actually very great if you want to get a low latency response. What about deep thinking? If you want to have deep thinking, obviously LLM, large language reasoning model are good if you want to have some mathematics and so on. What about vision? Obviously VLLM are great for this. And how about agents inside agents? So we said that SLM are actually great for this as well, but obviously the large action models are another great opportunities that can be used. So many products, the GPT backbone for dialogue, VLM for vision, HLM for long planning thinking can actually be used. If you enjoyed the video, make sure to like it. More importantly, subscribe to the channel so you get more videos. And if you are interested in the prompting, you can watch this one that I talk about 4 important prompts that you can use in order to get the most out of your needs. Or you can watch this one that's talking about the self-awareness of LLM by Anthropic. We're gonna be interested in knowing whether it is self-aware or not. Thanks for watching, and see you until the next one.